Hey, everybody.
Dr. Tran,
Yep, what's up?
for the geometry that's due, I think, on the 26th, is that including all the way up to the models?
Yes. Yep, so you should have
Okay.
pathing, segmentations, and models done by 26. Yep.
Okay, cool. Thank you.
Mm-hmm. Yeah, it's meshing is a complicated question, and so and I think what complicates things more is that there's different ways to measure mesh quality, um, and so what can happen with hexes is that because they can be distorted more than tets, people go a little bit crazy with that, and then they do some really crazy stuff with hexes, and so hexes can be squished really well, but they can't really be stretched all that much. And so what can happen sometimes if you have like a hex that like has to go like and do some weird stuff, that's going to cause a lot of issues with your simulation. Where if you try to do a tetrahedral mesh on that, then a tetrahedral might be able to do it a little bit smoother, where the elements aren't really as distorted. And so generally what you're looking for mesh quality is you want to see how distorted your elements are, which can be really hard to judge because like sometimes you might have a really distorted element on the interior of your mesh, and it's impossible to see just because it's on the inside. And so um, there's programs out there where you can test mesh quality. Actually, we can use PairView to actually test mesh quality. So PairView actually has a pretty good filter for that. And so normally, we use PairView like in this class to just view the simulation results, to view like pressures and velocities. But you can use it to check the quality of your mesh too. I'm sure ANSYS has some features that help you check for mesh quality too. And so, um, yeah. But a lot of softwares will define just kind of a nebulous mesh quality, but sometimes it's not clear exactly what that means. 'Cause sometimes it can be like sometimes people just use the aspect ratio as mesh quality. Some people take like the ratio of like the biggest area to the smallest area or something like that. Some people take some kind of skewness metric too. So there's lots of different ways you can measure mesh quality, which I think kind of complicates things quite a bit. Yeah. Yeah. Hmm. It does. Yes. It's definitely one of those things where it's not that it's you can teach someone definitely what to look out for a mesh, but it's like you kind of have to just see a lot of different meshes in order to really know what's like a good mesh and what's not. Um, and unfortunately it's one of those things that's like kind of problem specific too. Like a mesh might be really bad for like a fluid flow simulation, but it might be just fine for like a thermal simulation too, and it depends on the boundary conditions too. And so um, there's a lot. It's a complicated problem without a closed solution. Yeah, experience definitely helps a lot with those things. I should say, you have to experience seeing a lot of your simulations fail and being frustrated, like, why the hell did that happen? Before you really start to see, okay, that's probably why, that's kind of thing. Yeah, it's one thing to have someone tell you, but yeah, it's another thing to experience it, experience the frustration, get upset, curse, at least 3 times, and then that's when you know you understand something. Oh, that's the worst. Yeah, you buy it full price and then it goes on sale later. You haven't played it yet. That is a pretty crappy feeling. I'm better now. So I used to be really bad at that. I used to just buy, like, ooh, that looks nice. Ooh, that looks fun. And then I'll buy it because it's like 70% off. But then, yeah, just never play it. And then it's like, why is it? It's just taking up space in my Steam library. All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today?
Doing really well. How about you?
Good, good. Tired, but hanging in there. Yes, I was just telling my other class that I'm a little bit out of it today because my fiance brought me back a really nice mixed fruit tea, um, really late at night last night, and then I drank it, and then I had a lot of trouble going to sleep, and so I was. Um, for those of you who were in the last class, I was almost knocking out at some points in the lecture. So hopefully I make it through the lecture today just fine. But yeah, sleep is important. Sleep is good. Okay, and so today the plan is we're going to finish up our lecture notes on impedance of vascular networks, right? And so I don't think it's going to take us the entire time to finish everything. And so what I'm hoping for is to finish a little bit early and then help you guys out on the most recent homework because problems 3 and 4, probably it might throw you for a loop if you've never seen recursion before. And so I want to make sure I spend some time talking about that, especially how to structure the code, just so kind of hit the ground running for that. Okay. Okay, so besides the homework, we are coming up on the deadline for the geometry for your final projects, right? And so at this point, I think everyone in the class has image data that they're working with on the project. And so remember, on the 26th, what I want you guys to do is I want you to finish up all the way up until the modeling portion of the model. Okay, and so you should have the pathing done, you should have the segmentations done, as well as the model. Okay. And honestly, that's probably going to be where you're going to spend most of your time on the project. And so once you have the geometry done, then from there it's kind of configuring the simulation and writing the report. Okay. And so out of those 3 tasks, I would say that constructing geometry and writing the report are actually going to be the most time-consuming one. And then running the simulation will be actually pretty fast because we have that supercomputer that we've talked about before, right before the spring break. Okay. Okay. And so make sure you're working on your projects. And if you're having trouble, either constructing the model or just trying to figure out what the heck's going on in your image data, don't be afraid to reach out. So I think I think quite a lot of people have already kind of reached out and said they're not sure what they're looking at for the image data, or they're not really sure where to start. And so definitely hit me up if that's the case, because it's because it can be a lot. And so traditionally, looking at medical image data like this is something that people go to school for. And so, there's a whole profession called radiologists or radiology, excuse me, where people train to look at images, right? And so, we're engineers, and so we don't have that training. And so, it might be a little bit disorienting at first to, first open up that image data and just figure out where the heck to even start. And so, if you're struggling with that, don't be afraid to reach out, and I'm more than happy to help you guys out with that. Okay. All right. So any questions on anything before we get started? Okay. All right. And so we're going to continue our lecture notes on impedance and vascular networks. And remember, the goal of this unit is to basically take any kind of arbitrary, bifurcating tree. Okay. So let me draw my crappy kind of Christmas tree interpretation of blood vessels. Okay. So let's say that we have a blood vessel that goes like this. Okay. And then what we want to find is, what's the total impedance of this entire guy. Okay. Because if we can find the impedance of this entire tree, then we can learn a lot about, its wave propagation properties, as well as, a lot of other stuff as well. Okay. All right. And so if you remember, the way that we started with this is that we started with the 1D equations for blood flow, which is, what we derived last week. And then we linearized them, and then we kind of, massaged it a lot more in order to get it into a nice form. Okay. And so kind of skipping, a lot of those steps that we covered last time, what we ended up with was the following 2 functions. And so we had a flow function, Q1 of Z is equal to C1 e to the minus lambda t or lambda Z plus C2 e to the lambda z. All right, so that's the flow as a function of distance down the tree, okay? And we can also solve for the pressure as a function of distance. And it looks very similar to our flow. And so pressure is equal to minus rho, which is density, C0 squared times lambda divided by I omega A naught, okay, times minus C1 e to the minus lambda z plus C2 e to the lambda z, okay? All right. And where we left off last time was we have these two equations here, and we were in the middle of applying boundary conditions to solve for C1 and C2. Okay. All right. And so our two boundary conditions were one, that we knew the flow at the inlet, okay? And so we said that Q1 of 0 is equal to Q naught. Okay. And two, we know, we're going to assume that we know the impedance at the outlet. Okay. All right, so this is going to be P1 of L minus capital ZT times Q of L is equal to 0, okay? And then once we apply both of these boundary conditions, you know, we'll be able to solve for the two constants, okay? Okay, so any questions on this so far? So this is just kind of a recap of last time. Okay. All right, and so if we apply the boundary conditions, what we end up with is an expression that looks like the following, right? And so I think we were kind of right before we solve for C1 and C2. And so we solve for C1, and so C1 is going to be equal to Q naught, which was our prescribed inflow, plus over 1 plus gamma times e to the minus 2 lambda L, okay? And C2 was equal to Q naught gamma e to the minus 2 lambda L over 1 plus gamma e to the minus 2 lambda L. Okay. And so these were our two constants that we can go ahead and plug back in to Q1 and P1, okay? Where this quantity gamma right here, this was known as our reflection coefficient. Okay. And so the reflection coefficient was Z0 minus ZT all over Z0 plus ZT. Okay. Where Z0 here, this is the characteristic impedance of this vessel. Okay. And ZT, this is the terminal impedance. We'll review, you know, what all the different impedances mean in just a little bit. But basically, you know, I think we ended on this point that the reason this is called the reflection coefficient is that this reflects how, you know, the pressure waves are going to reflect, you know, in the cardiovascular system, right? And so, you know, I think before this, you know, we had always kind of said that, you know, whenever the pressure waves reach all the way to the end of the vascular tree, and so when it reaches all the way to the capillaries, that's when the wave is going to reflect back. But in reality, you know, you can have wave reflection that occurs way before you reach the capillaries, right? And so what this reflection coefficient told us was that whenever you undergo a change of impedance between one vessel to another, a portion of the pressure wave is going to reflect back. Okay. And so usually it's not a big number, and so usually the reflection coefficient is somewhat close to zero, but there is a little bit of reflection. If you think about how many bifurcations that you have in like a real life vessel, all those tiny reflections are going to add up. Okay. Okay. And so any questions on this so far? Right. And so I know this unit and the last unit too. It's a lot of terms, it's a lot of math, and there's a lot going on. And so I know. And so if I'm going to be perfectly honest with you guys, the last week and this week and next week too. Although I think next week's a little bit better. All these 3 weeks, this is kind of graduate level math stuff. And so this is traditionally taught for grad students. And so I know it's kind of a lot for you guys, and I'm not expecting you to know every detail of these derivations. And so what I'm thinking of of the way I'm going to kind of do the exam, which is in 3 weeks, is I want you guys to kind of take away kind of the important concepts from these derivations, right? And so there's not much we can do with calculations, just because a lot of these methods, they're like we've said, like they're designed to be computer algorithms. They're not really designed for human calculations. But what I really want you guys to get out of these is, what are the important concepts? And so what are things like, what does the reflection coefficient represent, right? And so what are the factors that drive on a wave reflection in the cardiovascular system? And so, those are the kinds of questions I want you to be able to answer in words, without really, without having to worry too much about the mathematical details, right? And so the math details, I show them to you just because, they're important to show you why these things are the case. But in terms of me assessing what you guys are doing in this class, the math details are not super important, right? I'm more concerned about what are the concepts that you guys are taking away, that you can apply some of these into your final project reports too. Okay. And so let's go ahead and move on. Okay. And so before we move into the actual algorithm of finding the impedance of a whole vascular network, let's make one more quantity. Okay. And so the last vocabulary word last type of impedance that we'll learn is called input impedance. Okay. And so input impedance, the way that we define that is basically just going to be the ratio of our pressure function and our flow function evaluated at z is equal to 0. Okay, so it's going to be P1 of 0 divided by Q of 0. Okay. And so if we evaluate that, then what we get is Z naught, which is our characteristic impedance, times 1 minus gamma e to the minus 2 lambda L divided by 1 plus gamma e to the minus 2 lambda L. Okay. All right. Okay, so now we have 3 types of impedances here. And so we have input impedance, characteristic impedance, and terminal impedance. Okay. And so the way input impedance is different is that this is kind of the impedance as seen from kind of the beginning of a vessel. Okay. And so you can almost think of this as like kind of the total impedance of everything downstream of this vessel. And so another way to interpret it is that, if you're a fluid particle and you're starting at the input of this vessel, by the time you reach, the end of the vessel, the input impedance is kind of like the total amount of impedance that you'll feel as you flow throughout the tree. Okay. Okay. Right. And as the fluid particle flows along the vessel, it will basically experience both the characteristic impedance and all the terminal impedances as well. Okay. And so let me draw kind of a figure just to kind of illustrate, the difference between all of these. All right. So let's say that we have just kind of a straight vessel segment here. Okay. Okay. And the way to kind of visualize these three impedances is that you have input impedance on the left, and this is where the blood is going to come into. Okay. Okay. Then we have Z naught, which is the characteristic impedance from this vessel in particular. And then we have terminal impedance, which is the impedance of all the vessels kind of downstream of this vessel. Okay. Right. And so I'll kind of write kind of more careful definitions for each of these, but I want you guys to kind of draw this figure here just so you can kind of see physically where each of the different impedances are located. Okay. Okay. So any questions on this so far? Okay. All right, and so let's go ahead and define, give a better definition for all of these impedances, okay? So actually, let's start from the right and work our way left. And so let's start with terminal impedance first. Okay. And so terminal impedance, remember, was ZT, okay? And so ZT is the impedance of impedance to flow at the end of a vessel. Okay. And so commonly, what the terminal impedance represents is the impedance for all the vessels downstream of this of wherever the outlet of this vessel is. Okay. And so basically, you can think of terminal impedance like this. And so if you have kind of a vessel that looks like this, right? Normally what you have for this vessel is that, after the blood leaves this particular vessel segment, it's going to go and split off into, all the other branching vessels, right? And so these are all the vessels that we you can think of them as that we don't see it in our, in our vessel, okay? But they're there, right? And so we have all of these, these are capillaries, arterioles, just downstream vasculature that exists outside of our model right here. Okay? And, because we have all these vessels down here, each of those vessels are going to impede the flow in their own way, okay? And so what the terminal impedance says that, instead of worrying about all these different vessels, we can, if we sum up kind of the total effect of all of their impedance, okay, then that's going to be the same as a terminal impedance. And so we can, instead of having, a big tree right there, what we can do is we can replace it with a single complex number called terminal impedance, okay? All right. And so usually this is something that's given to you in the problem because it's something hard to kind of solve for otherwise. All right, question. So is this similar to Thevenin's equivalence? Oh man, it's been way too long since I've covered Thevenin's equivalence, but from what I remember, yes. And so it's kind of almost the same thing as like equivalent resistances. And so I think that's kind of the same thing too, right? And so instead of having like a very complex kind of resistance network, that might look like this, right? Okay. Instead of having to worry about, all these different resistances here, we can sum this up into just kind of one resistance value, right? And so this is kind of the equivalent resistance, or the total kind of resistance of that. Okay. And so it's kind of the same thing. And so impedance and resistance, they're different, but they're kind of like two peas in a pod. Okay. And so the terminal impedance, you can think of that as the impedance of all the vessels that we don't see, right? Because they're kind of outside of our area of interest. And so it's kind of the same kind of concept that we use when we apply boundary conditions to our CFD model, right? And so if you remember, from our CFD workshop, for all the outlet caps for our CFD, we applied a resistance boundary condition, right? And what that resistance represents is all the viscous resistance of the vessels that are downstream of our 3D model, right? Because, it's right now it's practically impossible to run a CFD simulation on the entire cardiovascular system, right? Because you're talking about hundreds of thousands of miles of vessels that, ain't nobody got time to model all of those, right? And so the best thing that we can do is we can make a 3D CFD simulation for the vessels of interest, which are usually the bigger vessels, and then approximate all of the downstream vessels with like a resistance, okay? And so this is kind of the same thing, where instead of worrying about all of the vessels downstream, let's just sum it up into one number, which is terminal impedance, okay? All right. And so next we have the characteristic impedance. Okay. And so this was Z naught. Yes, Z naught. Okay. And so this is the impedance to flow that comes from a single vessel. Okay. And so, in the figure above, we're worried about everything downstream, but, our dude right here, this vessel, just by the nature of there being viscosity in here, this vessel itself is also going to impede some flow, right? And so what we can do is that instead of, and to basically kind of summarize the impedance of flow of a single vessel, we can sum that up into a single number as like Z naught, okay? And so that's why in the previous page, you saw me kind of I labeled Z naught as kind of, something that encompasses this entire vessel right here, okay? Because that's kind of what it represents. Okay. And so, if you kind of relate this to our idea of terminal impedance, you can kind of think of terminal impedance as kind of like the summed up effect of all the characteristic impedances of all the downstream vessels, okay? Because each individual downstream vessel segment will have their own characteristic impedance. And when you combine all their effects into one, that's how you get the terminal impedance, okay? Okay, so any questions on this so far? Okay. All right, and the last thing is just the input impedance. And so we call that ZI, okay? And so ZI, this is, you can think of it as the combined effect of the terminal impedance as well as the characteristic impedance for a particular vessel. Okay. And so normally for a vessel, you would have something like this, right? And so this guy, the characteristic impedance would be Z naught, and then everything downstream of this vessel we'll call it ZT, okay? If we wanted to club both of these guys together into one, okay, that would be input impedance Zi, okay? Right, and so input impedance, you can think of it as it gives us a tool to combine, downstream terminal impedances with the characteristic impedance of this particular vessel, okay? All right. And so, that's kind of a distinction between all the different impedances, because from here on out, knowing that distinction is going to help a lot, with the following example and with the algorithm that we're going to go over. Okay. All right. And so to kind of illustrate the algorithm, because remember our goal is to take kind of a very complicated network and find the total impedance or the input impedance of that entire network. Okay. And so to kind of start us off simple, let's start with kind of the simplest vessel network that we can think of, which is just a simple bifurcation. Okay. And so the bifurcation looks like this. Okay. Right. It's like a stick man without a head and arms. Okay. And so let's say that we know the characteristic impedance of all the different vessels. And so we'll say the characteristic impedance of the parent vessel is Z0 1. Okay. Characteristic impedance of the first daughter vessel is Z0 2. Characteristic of the third daughter vessel is Z0 3. Okay. Right. And let's assume that we know the terminal impedances as well. Okay. And so those will be ZT1 and ZT2. Okay. And so everything that I've written here in black is known, okay? And what's unknown here is Zi, which is this is the input impedance of this entire bifurcation. And that's what we want to solve for in this case, okay? All right. And so, given everything that we have in black, we can use that information as well as kind of the formulas that we have before to solve for, the input impedance of this entire tree, okay? Okay, so any questions on the problem setup? Okay. All right. And so, we're going to use all the formulas that we've covered up to this point, and we're going to use the fact that we have this bifurcation here, right? And we're going to use some rules for that bifurcation, because we've seen bifurcations before in our LPMs, right? And so we're going to use things like conservation of mass and continuity of pressure to kind of help us out to get our missing equations. Okay. All right. And so let me redraw the bifurcation here, okay? And let me draw, these quantities. Okay. And so those are going to be the flows in all the different vessels. And we also know the pressures in all the vessels as well. Okay. So we have P1, P2, P3, Q1, Q2, Q3. All right, and so if we look at this junction right here, what we can do is we can apply conservation of mass. Okay. And so conservation of mass basically says that Q1 is equal to Q2 plus Q3. Another thing that we know is that because these vessels are directly connected, then their pressures have to be the same as well, right? And so we also have continuity of pressure. Right? And so continuity of pressure tells us that all three pressures here should be the same, right? Okay, so P1 is equal to P2, which is equal to P3, okay? And so this kind of borrows from, what we know for the, from the LPMs. Sorry, lack of sleep. Okay. All right. And so we can use what we know about LPMs to basically combine the impedances of both the daughter vessels. Okay? And so if we take this information, what we can do is we can combine kind of the the impedances of both of these vessels. Okay? Okay. All right. Okay. And so if we define two new variables, and let's say that we define Zi2, and this is the input impedance of branch 2. Okay. And so that's basically the input impedance of this one right here. Okay. Okay. And we define the another input impedance called Zi3, where this is the input impedance of branch 3. Okay. What we can say is that these two branches here, because of conservation of mass and continuity of pressure, we can combine these two input impedances in parallel. Okay. Okay. And so what we can say is that 1 divided by ZID, where ZID here is kind of the combined input impedance for both of the daughter vessels. Okay. What that's going to be equal to is 1 over Zi2 plus 1 over Zi3. Okay. Right. And so this is basically just basically our parallel resistance formula. And so it's basically in the same way that if we have two resistors in parallel, we can find their equivalent resistance as 1 over R1 plus 1 over R2, and then we take just the inverse of that. Okay. Okay. And so that will take us, that will give us kind of the total daughter input impedance here at this kind of big green circle. Okay. And then one more kind of leap of logic that will help us is that is we say, wait a minute, if we can find the input impedance for both the daughter vessels at that green location, this is going to be exactly the same as the terminal impedance of the parent vessel. Okay? So this same as terminal impedance of the parent vessel. Okay. Right. Right. And so now that we have an expression for the terminal impedance of the parent vessel, then we can just kind of plug in the formulas to solve for the input impedance of the parent vessel, right? And so, I kind of went over the whole process kind of just very quickly in words right here, but I'll write down kind of every step kind of carefully on the next page. But I kind of wanted just to give you an overview of kind of where we're going and how we kind of formulate this this whole thing, okay? Before we actually kind of jump into it. Okay. So any questions on this before we really go into the steps of this algorithm in detail? Okay. All right. So let's jump into the details of this algorithm, right? And so the first thing we have to do is we have to compute the input impedances of both of the daughter vessels. Okay. Which we can do because what we're given in the problem is we're given the terminal impedance of each daughter vessel as well as the characteristic impedance of both daughter vessels. Okay. Okay. All right. And so let's go ahead and write out the formulas for that. Okay. All right. So first, let's do ZI2. And so ZI2 is going to be Z02 okay, multiplied by 1 minus gamma E, the minus 2 lambda 1 L or lambda 2 L2. Okay. And so L2, which is the length of that first daughter vessel, okay, all over 1 plus gamma e to the minus 2 lambda 2 L2, okay. Oh, sorry, this is a gamma 2, right? Where gamma 2, remember, gamma 2 is the reflection coefficient of that daughter vessel, right? And so gamma 2 is going to be Z02 minus ZT2, okay, divided by Z0 2 plus ZT2. Okay. Right, and so you can see why we need both the characteristic and the terminal impedance, because otherwise we wouldn't be able to compute gamma. Okay, and remember lambda is this quantity right here. Right? And so we have lambda is equal to, or lambda squared is equal to 1 over C0 squared times minus omega squared plus omega 8 pi nu divided by a. Okay. And so that was one of the constants that we derived kind of last time. Okay. All right. And so this is how we compute the input impedances of both the daughter vessels. Okay. And so you just kind of repeat the same thing for daughter vessel 3. Okay. And then once we have this, then we can combine them in parallel using the parallel formula on the previous page. Okay.
Professor?
Yep. Mm-hmm.
For the lambda equation, is that lambda squared?
Yes, lambda squared. Mm-hmm.
Would it be lambda 2 squared, or would it just be regular lambda?
This is just generic lambda.
Oh, got you.
Yes. Yeah. Mm-hmm. Yeah. So I think yeah. So the thing that makes this unique is that you have to plug in the area for this vessel right here, and so everything else I think is basically constant for this vessel. But in order to make this lambda 2, you have to plug in the area for this particular vessel. Yeah. All right. And so, you would have kind of the same set of equations for daughter vessel 3 as well. And so I'm not going to write it down, but you can imagine, it's kind of the same thing. Okay. Okay. And so, any questions on this? All right. All right. And so now that we have the input impedances of both the daughter vessels, we can then combine them in parallel, using our parallel formula. And so we saw this on the previous page, but let me kind of give you the overall formula, right? And so if you kind of invert that entire formula, what you get is zi daughter is equal to zi2 zi3 divided by zi2 plus zi3. Right, and so this is kind of what results when you combine those two in parallel. Okay.
Is that multiplied in the numerator?
Yes. Yeah. So those two are multiplied. Right. And so this is kind of the twist. And so this is kind of the thing that kind of connects everything together. So now that we have the total input impedance of the two daughters, what we can say is that this total input impedance is going to be the same as the terminal impedance of the parent vessel. And so we have ZT1 is equal to ZI D, okay. Okay. Right. And so now that we have the terminal impedance of the parent vessel, and we're given the characteristic impedance of the parent vessel, from there we can compute the input impedance of the parent vessel. Compute input impedance. Okay. And so basically you would follow just the same steps that we did on this previous page, right? So first thing you would compute is the reflection coefficient, right, for the parent vessel, which you can do now because you have both the characteristic impedance and the terminal impedance, right? And then from the reflection coefficient, you just plug it in into this formula right here to find the input impedance, and then away you go, right? All right. And so that's kind of the steps of the algorithm, okay? And then once you have the input impedance, you can go ahead and plug all of those things into into a lot of formulas. You compute kind of the flow distribution and the pressure one, okay? Okay. And so any questions on this? Okay. And so before we start jumping into the homework assignment, let me go ahead and let's kind of remind ourselves what impedance is, and generally what you can expect to from the results. Okay. Okay. All right. So we've used this term so much over the last two class periods, but let's kind of remind ourselves what it is, right? And what impedance basically is you can kind of almost relate it to viscous resistance, right? But the difference is that impedance represents the resistance to fluid flow that depends on frequency. Okay. And this is important because the whole concept of like viscous resistance, that's fine, right? So remember what we said that for viscous resistance was P, or delta P, we had our kind of our modified Ohm's law. So delta P was equal to Q times R. Okay. And so, we had this kind of a linear relationship here, right? And so this is fine for just a resistance, and this is fine if you have a rigid tube. But, in general, it doesn't quite follow this relationship in the cardiovascular system. Okay? And so in reality, real relationship between flow and pressure is not as straightforward as this, because it also it's affected by things like wall deformation. It's affected by inertia, and it also is affected by wave reflections. Okay. And so, it not only depends. And so basically, if you want to compute the pressure at a certain location within the cardiovascular system, it not only depends on the flow at that instantaneous time, it also depends on kind of the history of events that kind of led up to that time, right? Because what Ohm's law basically implies, that because Ohm's law is a basic algebraic relationship, is that Ohm's law implies that the pressure at any given moment depends directly on whatever the flow is at that given moment. But in reality, that's not the case, right? So it's not only what the flow is at that given moment, it also depends on wall deformation, inertia, and wave reflections. Okay, and so all these things basically imply that it depends on kind of the sequence of events, or the history of events that led up to that point. Okay. And so that kind of implies that our real sense of resistance, or real sense of impedance in the cardiovascular system, it has to have some kind of time component to reflect the fact that we have to take into account some events that happened before this. And so the fact that impedance here accounts for frequency, and it depends on frequency, does exactly that, right? And so impedance, you can almost think of it as kind of like a nuanced version of resistance, where it's it represents the same thing, but it's a lot more nuanced in what it represents, and how it impedes fluid flow. Okay. And so in particular, what I wanted to show you is a graph that shows the impedance of a vascular tree as a function of frequency. Okay, and I'll show you that on the next page. Okay, so any questions on this? Okay. All right, and so if you actually take this method right here, and you actually compute the impedance, and you graph it as a function of frequency, you'll see kind of the And so on the y-axis here, I have impedance, and on the x-axis here, I have frequency. Okay. And then what you'll see is that the impedance is usually highest near 0. Okay. And then it kind of tailors off from there. Okay. All right. And so, what this graph tells you is that when you have 0 frequency, that's when impedance is the highest, right? And when you have 0 frequency, that's called steady flow, okay? And so basically 0 frequency means that there's no oscillation in the flow waveform at all, okay? And so impedance is highest for steady flow. All right. Okay. And so now that we have a good understanding of what impedance is, and we kind of saw the example with the bifurcation, let's extend that example for the bifurcation to basically compute the impedance for an entire system of bifurcations, which is what was our goal originally for these nodes. Okay? And this kind of leads into kind of the algorithm that I want you guys to implement in problems 3 and 4 on the homework. Okay. All right. All right. And so first, so this is kind of a 7-step process here. And so a lot of these processes you'll see are kind of taken directly from the example. It's just that there's a one more step at the end until to kind of relate this to a giant network. Okay. And so remember, for a giant network, what I'm talking about here is a vessel tree that's more than just a simple bifurcation, right? And so we might say that this vessel bifurcates again, and these vessels might bifurcate again, and these vessels might bifurcate again, right? Okay. And so we have something that's really kind of complicated like this. And what we can do is basically repeat the same things that we did for the previous example over and over and over again until we kind of reach kind of the top here. Okay. But generally, the way that we're going to start is we're going to start at the endpoints of the tree, compute the impedances, and kind of collect them and kind of add them together until we reach the end. Okay. All right. So step 1. Oh, question?
Yeah. What's the unit on the y-axis again?
Oh, unit on the y-axis, that's impedance, and so that's Z.
Okay. Thank you.
Mm-hmm. Oops. All right, so step 1. So step 1 is to receive a gift. And so step 1 is to, you have to be given the terminal impedances of all the end vessels. Right. And so we're basically going to be starting at the ends of the tree and kind of working our way forward. Okay. All right. Step 2. And so step 2, given all of the terminal impedances and the characteristic impedances, actually, or you have to have a way to compute the characteristic impedances. Okay. Step 2 is to compute the reflection coefficient for all of those end vessels. Okay. All right. And so now that you know the reflection coefficient and you know the terminal impedance and characteristic impedance, what you can do is you can find the input impedance of each of the end vessels. so now what you have at this point is, this is kind of the same point that we reached in the example where we computed, the input impedance of both of the daughter vessels. Okay. Right. Okay. So any questions on this so far? Okay. All right. And so now that you have the input impedances of all the end vessels, you can combine them in parallel to find the kind of the terminal impedance of the parent vessel. Okay. All right. And so now that you have the terminal impedance of the parent vessel, then here it's a kind of a bunch of plugging in order to find the input impedance of the parent one, right? So step 5 is to compute the reflection coefficient of the parent vessel. Step six is to compute, once you have the reflection coefficient, is to compute the input impedance of the parent vessel. Okay. And step 7 is repeat this entire process until you reach the beginning of the network. All right. And so you can see that, because of this kind of repeat step, you can basically apply this algorithm to any size of bifurcating tree. Okay. And in fact, that's what I'm going to have you do on the homework. Okay. All right. And so, keep this algorithm in mind, because, this is basically what I want you to implement for the homework, right? But, what's going to be tricky about the homework is going to be the recursion parts. Okay. And so basically, the way I want you to do the homework is I want you to write it in a way where you can compute the total, either the total impedance or the total resistance for basically any number of generations in this Vascular tree. Okay. And so, if this is your first time doing recursion, then it's going to be a little frustrating, just because it's a little bit confusing. But let me go over it a little bit right now, just so that just to kind of help you out a little bit. Okay. If you look at the homework document, I also linked together a video that I think explains recursion really well. So definitely check that out. And then, but besides that, I'm going to go over it a little bit right now, just so that you can kind of see how it is. Okay. But before we do that, are there any questions on this? Okay. All right. All right, and so for the last 15 minutes today, let's go over recursion. All right. And so recursion is basically a style of computer programming where you define a function that's going to call itself. Okay. And so this is very unusual for a function to call itself, right? Because what's happening in the kind of under the hood is that you're writing your program, and then MATLAB's going to come across the function, and it said, okay, I'm going to call this function right here, and then it enters the body of your function, and then it tries to evaluate that function, and then by the end of this function, it said, call this function again. It's like, okay, call this function again. It goes back up to the top, right? And then it's kind of going to repeat. And so let me kind of visualize this for you, right? And so let's say that you're writing your MATLAB code, right? And so this is your code, code.m. Okay. And so let's say that you wrote your code, and then eventually you reach a point where you're going to run this function funct, and you're going to give it a value of x. Okay. Right. And so under the hood, what's happening is that MATLAB comes across this function called funct, and it's like, okay, let me go look in another file and see, let me see how funct is defined, right? Okay. Okay, and so usually what happens is that MATLAB will go into another file here called function.funct, right? And then it'll execute all the lines of code within that function, right? And so, if you've ever dealt with functions before, functions are basically a way for you to make your programming more compact. And so he said, basically, whenever you see me call this function, I want you to call this kind of batch of code that I've defined over here, right? And so it's kind of a way to say, instead of having a ton of basic lines of code into one file, you can define functions that, that kind of save you some space, okay? All right, and so normally what happens is that, you reach the end of this function right here, and then MATLAB executes all these lines in this function right here, and it's like, okay, I'm done, and then now I can go on my merry way right here, right, and go into the rest of the code, okay? Recursion is not like that, because what happens in recursion is that at the end of funct right here, you call funct again. Okay. And then what is MATLAB going to do when you call funct again? It's like, okay, I see funct. Let me come back up here and then just repeat the whole process, right? Okay. And so you enter this kind of what's called recursion loop where, where the function is basically calling itself, and it's kind of, the interpreter is kind of executing everything in the function and then returning to the head of the function and then calling it again, okay? And then you kind of always kind of enter this loop, right? Okay. Right. And so you can think of it a little bit like for loops, a little bit, but with recursion you can do a lot of other really fancy stuff that you can't do with for loops, right? And so that's kind of why it's kind of a technique, okay? But if you kind of see this this situation right here, this looks really bad, right? Because if you're kind of always constantly calling itself, right, then you're going to be stuck in this kind of infinite loop of get into the function, call itself, get into the function, call itself, get into the function, call itself, right? And so this is bad because you don't generally you don't want to crash your computer, right? And so you don't want MATLAB to run your RAM into the ground because that would be bad, right? And so a key part of recursion here is you have to code in a way to not only get into this loop, but also to break out of it. Okay. Okay. And so the way that you do that is you kind of have to do two things. Okay. First thing you have to do is you have to define a base case. Okay. And so a base case is basically a certain situation that you that you can encounter within the recursion loop that said, all right, so once I'm at this base case, then that's going to kick me out, right? And so once we reach the base case, that's it. That's the end of the loop, and then we can get out of here, okay? And so we need to find what that base case is and what to do in the base case, okay? And then the second thing that we need to do to break out of the loop is we have to make sure that every time we call the function again, we have to advance towards the base case, okay? So I should say each recursive function call gets us closer to base case. Okay. Right. And so a common way to break out of this loop right here is that, I wrote this func here with the x variable on purpose, right? And so the way that you break out of this loop is that when you recursively call this function, is that you don't call it with func of x, because if you do that, then there's no way to break out. What you call it in is you call it as funct x minus 1, okay? And so every time you call funct, then x is going to be reduced by 1, okay? And then eventually what you have somewhere in the body of this loop right here is that you have a situation when x reaches some kind of minimum value, right? And so let's say that we reach the base case when x is equal to 1, okay? And so when x is equal to 1, this is basically going to be our base case. And so there you can you can define what you do in that base case, and then and also kick yourself out of the loop. Okay, right? Okay. So any questions on this so far? This is kind of just introduction to recursion right here. All right. And so how does this apply to to our situation here? Right? Because in our situation, what we want to do is we want to compute the impedance of a very vast vascular tree. Okay. So the vascular tree might look something like this. And so I said very vast, but let's just take the situation where our tree bifurcates twice. Okay. And so starting with our parent vessel, then it's going to bifurcate into two daughter vessels, and then those two daughter vessels are each going to have their own little granddaughter vessels. Okay. And so we have basically, you can think of it as like three different levels of vessels here, right? So starting from the parent, we bifurcate once. That goes from the first level to the second level. And then once it bifurcates again, it goes from the second level to the third level, okay? All right. And so, what we want to do is like, let's just take the case where we want to compute the resistance of this entire tree. Okay. Right. Where where the formula for resistance, it's given by this formula right here. Okay. And so resistance is equal to 8 mu L divided by pi r to the fourth. Okay. And so this here is the resistance of a single vessel. Okay. And so we know how to compute the resistance of a single vessel, but we don't just want the resistance of a single vessel. What we want is the resistance of this entire tree, right? And so let's kind of design our solution strategy like this, right? And so since we know how to compute the resistance of a single vessel, let's apply this formula to all of the granddaughter vessels, or in other words, all of the end vessels. Okay. And since this is kind of a closed form problem where, you know, our end vessels don't have any children, right? And so this is going to define our base case. It's our base case because you can think of it as like, you know, since these vessels are the end, they're not going to have any kids. And so since they're not going to have any kids, then we can compute their resistance just straight up using this formula right here. Okay. All right. And so from that base case, you know, we can kind of work our kind of the same thing as we did with the algorithm, you know, that we talked about before. We kind of work our way back up to the beginning of this tree up here. Okay. And we're going to do that using recursion. And so since this is the base case, I'm going to say that, you know, the way that we compute all the resistances of these end vessels, we're going to call our recursive function with a value of 1. Okay. Okay. All right. So any questions on this so far? All right, so we're almost out of time, and so I'm going to work a little bit fast, right? And so now that we've computed the resistances of all of the end vessels, let's compute the resistances of their immediate parents, okay? And so let's compute the resistance of these guys right here, okay? All right. And so the resistance of these guys is going to be 1 over calc res 1 plus 1 over calc res 1, okay, because those are the end vessels, okay? And let's set this equal to the resistance of that whole thing, and so this would be 1 over calc res 2. Okay. All right. And so what we can basically say now is that you know, the resistance of this level right here, this will be calc res 2, okay? Right, and so you can see that we've gone 1 level up, okay? And so what we can say here is that when we call calc res 2, the function is going to recursively call itself to calculate the resistance of its end vessels and then kind of add that to itself, okay? Right? And then if we apply that one more time, and so we basically, you know, to find the resistance of this entire thing, what we can say is that the resistance of this entire thing is going to be calc res 3. Okay. And so you can see here, you can kind of see from this example here how we can kind of build up these kind of recursive iterations in order to get kind of the resistance of the entire problem. Okay. All right. So I think at the beginning of next week, I'm going to go over this again because we are, you know, a little bit over time because, you know, this was a little bit more rushed than I wanted to be. And so Tuesday, you know, we'll pick this up again and just to kind of make sure that everyone's kind of on the same page with the recursive algorithm. Okay. All right. So thank you guys for tuning in this week. You know, I'm sorry. I apologize for going a little bit over. Have a great weekend, everyone. And I'll see you guys on Tuesday.
Thank you, Professor. Have a great weekend.
Thanks. You too.
Awesome. Thanks, Professor.
Thanks.
Excuse me, Professor.
Yep. What's up?
I had a question on for my project. I'm
Yeah.
pretty behind, but I just can't get past this part. It's literally just the beginning because it's so close to